morning, Ricardo. All right. Good morning again, everybody. Those of you on joining us via YouTube Live, good morning. Good morning. Thank you for waking up again this Monday morning, and let's do some real work. All right. As exams get close by. All right. Without wasting much time, let's run through on our YouTube. I see Pamela Stabile. Good morning. Good morning. There's a whole lot of about 14 others who are also here. Good morning. Please, as you come in, just don't forget to like the videos. Those like really help us. Also, please help our social review. Just review. Tell us what we can do to improve. Okay. Okay, this morning, let's quickly jump into one of the topics where we could also get lots of marks in paper two as we build towards getting good marks at the end of the year. And I will be looking at chemical equilibrium. Okay, before I jump into questions, I will quickly, as the custom is, what are the definitions that I need to have when it comes to this topic? The definitions I must know. There are about four of them. Number one is to be able to define what a closed system is. All right. A system, we must be able, there are about four: closed system or open system. Number two, we must be able to define a reversible reaction. Let me quickly make a list. And remember, once I make a list, if we find these questions in our question, we just glide over quickly because we would have defined them here. All right. So please make sure your definitions are in. We cannot overemphasize the importance of those definitions. Hi, Catleo. Hi, Princess Lepoto. Good morning. Good morning. Good morning. Okay, just admitting some people in on the side. Awesome. You guys are morning birds. That's lovely. All right. So we have reversible reaction there as well, which we need to know how to define. Okay. The third one would be chemical equilibrium or dynamic equilibrium. All right. Chemical or dynamic equilibrium. This one, I will be giving you two definitions, which I need you to know. All right. I hope we are good. Okay, let's look at our definitions quickly. What is a closed system? A system that has no interaction with environment. A system that has no interaction with its surroundings, or environment. So we're basically saying it is isolated. A reversible reaction is a reaction where the products can be converted back to the reactants, where the products can be converted to reactants. All right. And I want to put a note here. This only happens. Okay. Chemical equilibrium. I'll put it here. Chemical equilibrium. What is chemical equilibrium? I said there are 4 definitions. The last one would be Le Chatelier's principle. Chemical equilibrium is a state where the rate of forward reaction, please, I'm going to write this in capital. Let us forget that. All right? Rate is not the forward, it's the rate of forward reaction is equal to the rate of the reverse. Don't put the word rate, then the whole thing is wrong. Reverse reaction. Or we should, let me put this in yellow or green, a state where the concentration of products and reactants are constant. Let me put that word in capital. Are constant. Okay. Then last one is excuse me. Last one is the famous one, which would definitely be tested. And what is that? That is Le Chatelier's principle. All right. Le Chatelier's principle. You and I know that there is no way we are going to run away from this question of defining Le Chatelier's principle. It will definitely be tested. All right. What is Le Chatelier's principle? When the equilibrium, all right, in a closed system is disturbed, okay, this can only happen in a closed system, all right? The system will reinstate a new equilibrium by favoring, okay, a new equilibrium by favoring the reaction that opposes the disturbance, or let's say that will cancel or oppose the disturbance. So in physics, we would have said what? Newton's third law. If we're doing physics, we would have said the action reaction principle. All right, guys, please, a quick word here. This only happens in a closed system. This only occurs in a closed system. If the system is not closed, we are not going to have that. All right, quickly. What are the conditions or the disturbances that we can have? Just going to make a list and then we jump into our questions. What are the disturbances that we may have and how. All right. Basically, there are three disturbances that we can get. All right. There are basically three disturbances. Three of them. All right. Three disturbances. Number one, concentration. Just going to put a statement for you here to say an increase in concentration of one of the reactants. Now, please take note. We are now saying the reactants. I want to make it general for you. Now I have mentioned the word reactants. Okay? Will cause equilibrium to shift to the left, or to the right rather. Equilibrium to shift to the right. Favoring the forward reaction. I'm just explaining now quickly. Favoring the forward reaction. In bracket, what are we using? We are using up the excess. All right? We are using up the excess reactant. Why excess? Because it increased. Okay. Favoring the forward reaction, so it will shift to the right, favoring the forward reaction. And more products will be formed. More products will be formed. And you can use this as your yardstick. You just change increase. If it was a decrease in concentration, all right, what happens? This will cause the equilibrium to shift to the left. Let's write that. A decrease in concentration of one of the reactants. So you would use this to move around that of the product. All right, will cause equilibrium. Equilibrium shift to the left. And if it shifted to the left, what's happening? We are favoring the reverse reaction. Favoring the reverse. Why are we favoring the reverse reaction? To make up what is lost. So the ones in bracket are to guide you. To make up what was lost. Remember, we said it decreased. All right, the other one increased. We want to use what was in excess. Now we want to make up for what is lost. That's why it's going to favor the reverse reaction. All right, I just want to shift this. Make up for what was lost because of the decrease. Okay, therefore, more reactants will be formed. More reactants will be formed. Okay, a change in concentration, does not affect the Kc value. We're going to talk about the Kc value. All right, for now, I am done with concentration. Just a short note there to guide everyone. Read that and you'll understand how concentration changes behave. All right, that's my first disturbance. There are three of them. Can I quickly look at pressure? Disturbance number two, pressure. My writing now because I'm rushing. Pressure. Now, please, whenever we talk about pressure, these affect gases only. An increase in pressure, which is basically a decrease in volume. So please understand the relationship between them. Examiners will sometimes not tell you about the pressure, but they will refer to the volume. All right? Will favor the side with fewer number of moles. Side with fewer, or the side that produces fewer number of moles. Let's say favor the side, I want to use the word that produces. Favor the side or the reaction, let's use that, favors the reaction that produces fewer or lesser number of moles. Now, a lot of people stop here, and I feel that is wrong. Just not the number of moles. It has to be number of moles of gases. Please take note. Okay, a change in pressure, a change in pressure does not affect what? The Kc value. All right? A change in pressure does not affect Kc value. Now, a quick one here is this. When pressure changes, the rate of both reactions, when I say both reactions, I mean both the forward and the reverse, forward and reverse, all right? The rate of both reactions is affected, but the favored one, is more affected. All right, remember under rates of reaction, increase in pressure increases the rate of reaction. Increase in pressure increases the rate of whether fewer number of moles or not. So please take note. When pressure changes, the rate of both reactions, forward and reverse, is affected, but the favored one is more affected. Both of them are affected. You'll see if we get to a graph. Increase in pressure increases because increase in pressure increases the rate of reaction, whether it is forward or reverse. But the one that is now affected based on equilibrium will be more affected in terms of the number of moles of gas that is produced. Okay, number three. Number three. Number three. Number three would be temperature. Temperature. Now, you and I both know that for temperature, we have what we call exothermic and endothermic reactions, right? Here, delta H is less than 0, delta H is greater than 0. Here, delta heat is our reactant and product. All right, exo, heat is released. We are saying heat is also a product. Here, heat is absorbed. And if it is absorbed, we're saying heat is a reactant. So take note of the languages that the examiners would use. All right. Now, increase in temperature when it comes to equilibrium favors the endothermic reaction. And you can just reverse that statement. Endothermic what? Reaction. However, an initial increase in temperature, an initial increase in temperature increases the reaction, increases the rate of reaction, increases the rate of reaction, no, of both reactions, of both. When I say both, I mean forward and reverse. I'm now using rate of reaction topic. All right, reactions, but the one affected the most is favored. The one affected the most. All right, an initial increase in temperature, an initial increase in temperature will increase the rate of forward and reverse reactions. Okay, since I've said increase, let's be specific. Since I'm using the word increase, let me underline that. An initial increase in temperature will increase the rate of both forward and reverse reactions. However, the endothermic reaction increases more than the exo. That's what we mean. Both of them are affected because this statement will, help us appreciate how to read graphs. Both of them are affected, but one is affected more than the other. Kc value is also affected. This is the only factor by a change in temperature. All right, I have 5 minutes more about to just write one more statement. Now, there is a particular question that I see, 4 marks, that a lot of learners, all right, usually miss. A lot of learners usually miss this. I quickly want to attack that question based on temperature. All right, let's do this. I'm going to just create a hypothetical situation, and then you can use that to build the other one. So I'm only going to use one situation in this case today. Let me just make sure that I have the correct page. Lovely. Okay. Effect of, let's remove this disturbance. Effect of temperature change on Kc. Now, learners don't know how to identify whether a reaction is forward or reverse. Okay? Learners don't know how to identify whether a reaction is forward or reverse. Okay? Let's say, for example, consider A plus B, all right, to give us C plus D. And we don't know delta H is unknown. All right, we don't know whether it's exothermic or endothermic. Okay, the conditions that we are going to consider are this. Kc value increased. I'm just creating one. All right, as temperature decreases. All right, what will be my answer as temperature decreases? Okay, is the reaction exo or endo? How do you attempt this question? First is to talk about Kc value. Okay, if Kc value increases, all right, if Kc value increases, it means that more products are formed. All right, take note of that. If Kc value increases, more products are formed. All right, if Kc value increases, more products are formed. All right, somebody was typing a message. Sefuto, are you okay? I was trying to read your message and it was deleted. Okay, if Kc value increases, more product, please take note, more products are formed. And for more product to be formed, all right, that's the first statement there, the forward reaction is favored. That is the impact. Okay, more products are formed, product is forward. So the forward reaction is favored. Okay, now we've spoken about Kc. Let's go check the temperature. What happens? Temperature was decreased. And I know that an increase in temperature favors the endothermic. We mentioned that. But here, what are we doing? We decrease temperature. Okay. A decrease in temperature favors the exothermic. Oh, guys, once you get to this point, we are done. And I'll show you what I'm going to consider. Only two things are favored. The forward reaction is favored. The exothermic reaction is favored. Therefore, forward is exothermic because both of them are favored. The forward is favored, the exothermic is favored. It's 4 marks there. 4 beautiful marks. All right. Just want to quickly mention something here. We know Kc expression, all right? Kc expression, then we jump into questions. I think I have 3. All right, this is not a formula, so it's the ratio of concentration of products to that of reactants. That of reactants. That's why it doesn't have a unit. Product. Okay, lovely. All right. If Kc value is greater than 1, it means the forward reaction is favored. Forward reaction favored. And when we say forward reaction, it means we have what? More products. And a quick way to look at that is to look at the sign. It's an inequality sign. Where is it pointing to? It is pointing to the forward side. That's quite clever. When Kc is less than 1, already you can tell me what's going to happen. The reverse reaction is favored. And what does that tell me? That tells me more reactants are formed. All right, guys, let's jump into questions quickly. Let's jump into a few questions quickly. I hope we are good so far. 30 minutes was just for summary. Let's jump into questions. Kc. Now, somebody's worried about, somebody's worried about catalyst. And let me quickly clear the air for you. Catalyst. Somebody's really worried that, okay, when it comes to chemical rate of reaction, we do talk about catalyst. All of a sudden, it's silent when it comes to chemical equilibrium. Let's talk about the effect of catalyst on equilibrium. And some of you might not even have, gone through this. Okay, catalyst increases the rate of both forward and reverse reaction simultaneously. All right, simultaneously. Hence, equilibrium is not affected. That's why we don't count it as a disturbance. Equilibrium is not affected. So is Kc. So you would probably get a graph that looks like this. Rate of reaction, and you have time. So usually we use dotted lines and okay, so we have that and we have dotted lines. Now, these parallel lines means we are already at equilibrium. Now, at this time, let us add a catalyst. At T1, let's add a catalyst. Now, what do we say? A catalyst will increase the rate of reaction. Okay, Rich Height, you cannot just look at a reaction and tell whether it's exo or endo. There must be information given. You said, how can we tell whether a reaction is endo or exo? By just looking at the equation where there is no change in enthalpy. They will tell you, don't worry, they can't just leave you hanging. But you need to read carefully. Sometimes they say heat is a reactant or a product. I wrote something there. You see, if they say plus heat as a product, then it is exo. If they say plus heat as a reactant, then it is endo. But without that, they cannot just ask you, except if the reaction is combining with oxygen. For example, if I tell you A plus oxygen to give you whatever, this is automatically exo. Why? When something is reacting with oxygen, it is combustion. That's burning. Okay, so those are the little things, but otherwise, you will be told. I hope that makes sense. All right, let me clean this. I hope you got that. So they will tell you, don't worry, they're not wicked people. There's always information. You might miss the information, but it is always there. If you have any question like that feels unfair, please send it and let us discuss together. All right. So if we now add catalyst, what will happen? Both reactions are favored equally. Both reactions are favored equally at the same rate. So none is favored more than the other. All right. Are we okay there? That is our catalyst there. All right. Catalyst increases both the rate of forward and the reverse reaction. Is that okay? Both the rate of the forward. That's why catalyst is not involved here. So that is what your graph will look like. Awesome. Because we're saying, remember, dynamic equilibrium is the rate where the forward and reverse reactions are constant. So that is done. Guys, why is this one starting from 6.3? Why is this question starting from 6.3? Oh my God, what happened to All right, just one moment. Let me see. Oh, yeah. Let's drag this part down. It needs to be right here. Okay, quickly. 1 mole of hydrogen iodide gas, HI, is sealed in a 1 dm cube container. Please make sure you read that. All right? In a 1 dm cube container, and take note of the temperature at 721 Kelvin. Take note of that. Okay, this doesn't tell us whether it's exo or endo yet. Okay, we don't know whether it's exo or endo. We just know the temperature. Equilibrium is reached according to the following: balanced. Now, please look for this word for me. It must be sealed. If it is not sealed, we cannot have chemical equilibrium. Now, one question I want us to quickly deal with here is type of equilibrium. This is a homogeneous equilibrium. Why? Reactants and products are in the same phase. Reactants and products are in the same phase. So please, that's another definition. If it is not, if they are not in the same phase, it is called heterogeneous. All right? If they are not in the same phase, it is called hetero. Phase means gas, 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 phases of matter. All right. It is found that, please, I need you to read this. I don't know why we don't take time to read. It is found that 0.11 moles, very important, is the unit. 11 moles, all right, of hydrogen iodide are present at equilibrium. Okay, cool. We are done with the first one there. Determine the number of moles of each of the following at equilibrium: H2 and HI. All right. Determine the number of moles of each of the following at equilibrium. Okay. Look at what we have, guys. We are told that it is found that 0.11 moles of that is found. All we need to do is to use our mole ratio. Here, you have H2 and then you have what? I2. We were given 0.11 moles here. Remember, this is 2 to 1 to 1. Let's use mole ratios. If this is 0.11, this is also going to be 0.11. That's why 1 mark there. And this is 0.22. All right? Are we okay there? Awesome. Let's quickly go now because I know we want to look at the table. All right. The equilibrium constant Kc at 721 degrees is 0.02. All right. Let's quickly look at that because I know that Kc most times are the challenges that we have. It says the temperature of the container is now increased. That's why I said that it is important to take note of the temperature change. Please don't just read through. Take note of the temperature change. The temperature of the container is now increased. The equilibrium constant Kc is now 0.09. Guys, I have already answered this type of question when I was explaining. I have answered this question when I was explaining. The examiner wants to give you some 4 free marks that you and I must definitely get. All right, you and I must definitely get this question. Okay, let's quickly answer. We are not going to waste any more time in just copying and pasting the answer that we already have. You and I have this answer already. Okay, you and I have this answer. It's the forward. Please, guys, you've got to answer your question first. So you've got to answer with the reason first before you answer whether it's exo or endo. So you'll see what I will do. I would leave that point. I'll go to 6.3.2 to answer my question first. All right, I go to 6.2 to answer the question first to determine whether it is exo or endo. All right, you determine whether it is exo or endo by explanation before you jump into the answer. All right. The equilibrium constant, what happened? It increased. Okay. From 0,02 to 0,09. All right. Kc increased. What does this mean? This means more products. More products are formed, right? Lovely. For more products to be formed, it means that the forward reaction, always keep on what is favored. Forward reaction is favored. Beautiful. Please always, always do that. The forward reaction is favored. Interesting. Now, if the forward reaction is favored, how then do we deal with the rest of the answer? Fully explain. We are explaining now. Remember, I have not yet said whether it is exo or endo. Let's see what happened to temperature. Temperature also increased from 721 to 850. There is only one statement you need to know here. An increase in temperature will favor the endothermic what? Reaction. Please don't forget that statement. That statement is key to anything you and I will be doing. Increase in temperature favors the endothermic what? Reaction. Let's write that down. Increase in temperature. Remember what I said. Always write what's favored. Increase in temperature favors the endothermic reaction. Now, if you look at, we've used the word favored twice. Endothermic is favored, all right, and the forward is favored. Is the reaction forward? Is the reaction forward reaction exo or endo? Already we see that our forward reaction is endo. Forward reaction, all right, is endothermic. So I'll come here now and put the word endothermic here. It's a negative marking in the exam. If you get 6.3.1 wrong, examiners no longer mark the rest of the questions. Okay. What are we saying here? Okay, Sefoto says more products are formed, but Kc is less than 1. Yes. In this whole reaction, okay, let me explain that. In this whole reaction, Kc is less than 1, right? So originally, because Kc is less than 1, the reverse reaction, reverse is favored. That's the original stuff. Okay, we are simply saying more products are still formed. Even when Kc goes to 0,09, more, more reactants are still formed. All right, it's just that the quantity formed at 0,09 is more than the quantity formed at 0,02. Please let's get that before we continue. Kc is less than that. Reverse reaction is favored. But we are now saying that Kc value has increased. Is that okay? So this time around, we are now shifting to the right-hand side, but it doesn't mean that the quantity of product is still more than the quantity of reactants. The quantity of reactant is still more, just that at different ratios now, at different temperatures. I hope that makes sense. All right. So please take note of how the question is answered. Forward, more products are formed. You can even write equilibrium shifts. I like to always add that. Equilibrium shifts to the right. I hope you understand what I'm saying now. Equilibrium shifts to the right to form more products. Equilibrium shifts to the right. But it still forms product. Yes, it is now more compared to the previous, but it's still less than the reactants. Okay. Calculate the mass of hydrogen iodide gas at the new equilibrium. At the new equilibrium. Okay. Easier here to use a table, which most of us know how to deal with. Let's quickly get that table done, and then we go back and check the information that we have. All right, you and I know how to draw the table, and I'll quickly clear one error that people normally make on the table as well. Let's see something here. But to go back to read, okay, we know people say rice, it's not really rice. It's equal number of moles, change in number of moles, and fire the equilibrium number of moles, then equilibrium concentration, which is number of moles divided by volume. That's very important. I like to write my volume, and this is how I like to rule mine. And all right, and we all have different systems, but what works for me? Okay, it is hydrogen iodide, it is iodine gas, and hydrogen gas. It's two ratios. Let's quickly go back now and read. Sefoto, I am just waiting to read from you. Okay. Just to make sure that you are okay with what we said, so that I don't leave you hanging. Can quickly just respond before I move on. That would be nice. Otherwise, you can send a message and I'll come back to your. All right. I hope everybody's okay as well. Any questions so far? If there is, please let me know. Just let me know. All right. Okay. Oh, there was something I didn't finish here. Right, hold on. Determine the number of moles of each of the following. Six, let me just write the answers here. 6.2.1. Hydrogen gas will be 0.11 moles per cubic what? Decimeter. 6. Now check. Hydrogen iodide. We are actually having 2 moles there, 0.2, but we started, remember, 1 mole of pure hydrogen iodide gas was present. Is that okay? Now we have only used 0.22. Then the question says determine the number of moles of each of the at equilibrium. Okay, at equilibrium, it's the leftover, the concentration of hydrogen iodide. Hydrogen iodide will be 1 minus 0.2. That should actually give us 0.78 moles per what? Decimeter. All right, so the mole ratio there is a guide. Oh, number of moles, not concentration. Number of moles. Sweet. All right, I came here to pick the information we have. We have 1 dm cube as volume, okay? That is our volume, 1 TM cube. Now, let's check something here. Please, I want us to listen to this particular question very well. All of this happened at 721 Kelvin. Look at the question. Calculate the mass of hydrogen iodide present at the new equilibrium at 850. It means we are now working here at 800 Kelvin. The question is, where did we start from? We started from 721. Please, I want you to listen carefully to the table here. What is the initial number of moles before we got to this equilibrium? This is when learners miss it. We don't read carefully. This is 0.11, 0.1 attained at 720. The Kc we want is at 850. We made the change at 721. Now we want a new equilibrium at 850. Okay. I don't know the change. Is that okay? What we know right now is we are given Kc, and Kc is 0, right. This is how I'd like to do it. Since we don't know the change, let the change be x, okay? Let this be x. What we do is we cross multiply, and this is how I like to do it. I'll write my A here. I'll write my B. You put x anywhere, but I'm trying to avoid fractions, okay? I could put the x anywhere. Thank you, Sefoto. Beautiful, beautiful. All right, I could put the x anywhere, but I'm trying to avoid what? Fractions. Please take note, it's not always zero. You got to read. Now, how do I cross multiply? I'm going to use highlighters. It is, we call it rice, right? But I like to say rice is nicer when it is eaten. Rice and chicken. R and C. Okay, it's too early to get hungry. Rice and chicken. Check. I am going to cross multiply. X times 1 is x, and 1 times b is b, right? So, what x? It is x times 1, which is 1, and b. Lovely, because it's the same mole ratio. Sweet. We are looking for a now. Can we quickly do the same thing? Same thing. 1 times a is a, and times x is 2x. If we apply, do you notice a would be equal to 2x? And we are done there, my learners, very fast. 2x. Now, reactant will decrease while products will decrease, product will increase. What will this be? 0.78 minus 11 plus x, 0.11 plus x. What is concentration? Number of moles divided by volume. And my volume is 1. So what do we have? Oh, this x over 1 will remain as what? 0.78 minus 2x. Right? 0.11 plus x, all over 1 over 1. Now we can write our Kc expression. What is our Kc expression? Kc expression would be that of the reactants, Hi, but this one, that's a squared. What is our Kc value? We are done with this question. 0.09. Hydrogen at equilibrium concentration. 8. Hydrogen iodide. Yeah. Hydrogen is what? 0,11, all right, plus x, and I have now changed my bracket, 0,1 x over, what about hydrogen iodide now? 0, minus 2x, all what? Squared. Remember, I said do not foil here. Is that okay? Do not foil. What do? We can then write this 9 equals to 0 x squared over 0,7 x squared. We did this under electrostatics. If you remember, we said that we use the principle squared over b squared, a over b. All right, so what would I have from here? What would I have from here? I hope the table makes sense. Please, always zero, like most questions would be. Okay, now let's quickly mathematically solve this. Unfortunately, we are only going to do one question today. 0,09 over 0,728. Let's find the square root of both sides. Let us find the square root of both sides. Okay, I need to brush this because I know I struggle with that. This would give x over 0, what do we then do from here? We can now do maths where we cross multiply. All right, let's cross multiply. What are we going to have? 0, writing everything out so that while you are revising, you can see. Okay, for the first time today, let me get my calculator. 0,3 multiplied by 0,78. Let's see. 4 minus 0 x equals to 0,1 plus x. All right, let's bring all the variables to one side. 0,234 minus 0,11 will be x plus 0,6x. This would give us 0,124, and this will give us 1,6x. Okay, let's see. What is 0,124 divided 775? This is, don't let us round 775. Let's go check. What is it that we are looking for again? Let's see the x. Calculate the mass of hydrogen iodide present at the new equilibrium. At the new what? Equilibrium. Now, what did we say our x was? X is the quantity here of HX that was used, all right? H2I2. Now, at equilibrium, look at what we have, guys. This is what we have. We are looking for the mass, all right? So let's make this very easy. The mass of hydrogen iodide. What do we know, guys? Mass over molar mass. So the number of moles at equilibrium. That's going to be the question. Do we know the number of moles at equilibrium? Yes, we do. We can, because molar mass we are going to get from our periodic table, the number of moles of this at equilibrium. it was 0.78. All right, minus 2x. 0, minus 2. Let's see what we are going to get quickly. The number of moles at equilibrium. 0.78 minus 2 times 0.0775. All right, we have 0.625. Beautiful. 0.5 moles at equilibrium. 0.775. This is the number of moles at equilibrium. Right, I'm rounding up now, guys, getting our 8 marks there. But the question wants the mass. Mass equals to number of moles multiplied by molar mass. So 0.5. What is the molar mass of hydrogen? Hydrogen is 1, and iodine is actually 127. All right, I don't have a periodic table here, but it's something that check a periodic table. You should be able to confirm that for me. 0.65 multiplied by 128 would then give us what? 80 grams. 80 grams. All right, guys, this is how far I can take you this morning. Please take note of the changes in equilibrium. I am really asking for you to read, okay? Take time to read and get that equilibrium correct. All right, guys, this is how far we can help again this morning. Thank you for all the likes. Again, the review page link is shared. Please just like, share, and let someone also enjoy the session. I will be seeing you here again tomorrow. Have yourselves a very lovely day, and we'll be looking at optimization of calculus tomorrow. And on Wednesday, we will be looking at photo effect. All right, guys, keep well. And I know many of you will be doing your pledges today. Good luck. Do it with your heart. And God bless. Make sure you leave a comment on our review page. We would really appreciate that comment. It means a lot to us to hear from you, and you tell us what we can do to serve you better. Our aim is always to make you. Bye, everybody.